Propositions and taxonomy of spaceships on design structures. Significant parameters for elements interactions. In the standard periodic table there is a tabular arrangement of the chemical elements, organized on the basis of their atomic number, that is the number of protons in the nucleus, electron configurations, and recurring chemical properties. The rows of the table are called periods, the columns are called groups. Elements in the same group tend to show patterns in atomic radius, ionization energy, and electronegativity. When atomic radius decreases, then ionization energy increases and electronegativity increases. From top to bottom in a group, the atomic radii of the elements increase. Since there are more filled energy levels, valence electrons are found farther from the nucleus. The lower the values of ionization energy, electronegativity and electron affinity, the more metallic character the element has. Neutrons as significant parameters for elements interactions. While protons define the entire charge of a nucleus and, hence, its chemical identity, neutrons are electrically neutral, but contribute to the mass of a nucleus to nearly the same extent as the protons. Neutrons explain the phenomenon of isotopes. Varieties of the same chemical element, which differ only in their atomic mass, not their chemical action. The neutron has a positively charged core of radius approximately 0.3 fm surrounded by a compensating negative charge of radius between 0.3 fm and 2 fm. The proton has an approximately exponentially decaying positive charge distribution with a mean square radius of about 0.8 fm. The largest known completely stable to alpha, beta, and gamma decay nucleus is Lead-208, which contains a total of 208 nucleons, 126 neutrons and 82 protons. Nuclei larger than this maximal size of 208 particles are unstable, and as a trend become increasingly short-lived with larger size, as the number of neutrons and protons, which compose them increases beyond this number. However, Bismuth-209 is also stable to beta decay, and has the longest half-life to alpha decay of any known isotope, estimated at 1 billion times longer than the age of the universe. Elemental interactions and structures. In space vacuum temperature, that is -273.15 Celsius, elements up to 88 atomic number can preserve their solid-state structural stability. There is an exemption for the helium element, due to its critical superfluid behavior, around to this specific vacuum temperature. But even for the most exotic material strength capabilities, there are limitations. Let's see the case of neutronium. As you may notice, the periodic table counts progressively the number of proton inside the nucleus. However, for educational purposes we have to refer to the case of neutronium, a substance that is composed only by neutrons, the element with atomic number 0. Extremely dense substances resembling the neutron degenerate matter, theorized to exist in the cores of neutron stars, henceforth degenerate neutronium will refer to this. Free neutrons decay with a half-life of 10 minutes, 11 seconds. A teaspoon of degenerate neutronium gas would have a mass of 2 billion tons, and if moved to standard temperature and pressure, would emit 57 billion joules of beta decay energy in the first half-life, with average of 95 megawatt of power. In order to store and preserve such a hypothetical reaction, the structural storage chamber of the spaceship energy compartment should sustain such an enormous structural load initially for the 2 billion tons gas overall weight, while the transition temperature flow load, to handle the energy released to this period of decay time, would eventually put in critical condition any advanced material integrity. Elemental interactions and structures. Also, the manipulation of such a released energy into a transformation power, in order to serve the energy needs of a spaceship, also constitute a major concern. It is also possible in cases for nuclear reactions, whenever they have produced inside or outside a spaceship compartment, to create navigation instabilities, like gravitational interactions, magnetic disturbances, or instruments miss-out performances. To handle structural integrity for propulsion and navigation for spaceships designs, extracting nuclear energy, the elemental solid-state stability of the materials is not enough for structural operation safety. The Pauli exclusion principle disallows two identical half-integer spin particles, electrons and all other fermions, from simultaneously occupying the same quantum state. The result is an emergent pressure against compression of matter into smaller volumes of space. Electron degeneracy pressure results from the same underlying mechanism that defines the electron orbital structure of elemental matter. In the presence of atomic matter compressed to the state of electron degeneracy, the dash decay may be inhibited due to Pauli exclusion principle, thus making free neutrons stable. Also, elevated pressures should make neutrons degenerate themselves. Compared to ordinary elements, neutronium should be more compressible, due to the absence of electrically charged protons and electrons. So, concepts of compression can control energy releases, contributing significantly to structural requirements for performances. Elemental interactions and structures. This makes neutronium more energetically favorable than positive Z atomic nuclei, and leads to their conversion to degenerate neutronium through electron capture, a process which is believed to occur in stellar cores in the final seconds of the lifetime of massive stars, where it is facilitated by cooling via V emission. As a result, degenerate neutronium can have a density of 4 multiplied by 10^17 kg per meter cubed, roughly 13 magnitudes denser than the densest known ordinary substances. It was theorized that extreme pressures may deform the neutrons into a cubic symmetry, allowing tighter packing of neutrons, or cause a strange matter formation. The concept of packing neutrons inside a nucleus in a cubic form opens new insights for energy-matter relations. The closure of the stable shells predicts unusually stable configurations, analogous to the noble group of nearly inert gases in chemistry. An example is the stability of the closed shell of 50 protons, which allows tin to have 10 stable isotopes, more than any other element. The picture of a nucleus as a drop of incompressible liquid roughly accounts for the observed variation of binding energy of the nucleus, volume energy. When an assembly of nucleons of the same size is packed together into the smallest volume, each interior nucleon has a certain number of other nucleons in contact with it. So, this nuclear energy is proportional to the volume. Surface energy. A nucleon at the surface of a nucleus interacts with fewer other nucleons than one in the interior of the nucleus, and hence its binding energy is less. This surface energy term takes that into account, and is therefore negative and is proportional to the surface area. Coulomb energy. The electric repulsion between each pair of protons in a nucleus contributes toward decreasing its binding energy. Asymmetry energy, also called Pauli energy. An energy associated with the Pauli exclusion principle. Were it not for the Coulomb energy, the most stable form of nuclear matter would have the same number of neutrons as protons, since unequal numbers of neutrons and protons imply filling higher energy levels for one type of particle, while leaving lower energy levels vacant for the other type. The combination of elements for materials and structures that can be used as taxonomy. Under the broad term of a structural synthesis for spaceships designs. Energy needed for a spaceship can determine a design concept based on the energy system usability, that is based as a system energy extraction and transformation for various spaceship energy needs. The basic requirement is to configure the energy packing fuel storage, and to feed the process energy production systems. You may envision nucleus as liquid draw packing where atomic radius for packing nucleus is the major concern. Upon specific pressure conditions and operation temperatures that can predetermine ionization energy and electronegativity characteristics that are affecting the chemical reactions and bonding reactions for the structural material selections. Considerations for potential relativistic behavior of heavy atomic nucleus in a spaceship reference frame. The relativistic Dirac equation has problems for elements with more than 137 protons. For such elements, the wave function of the Dirac ground state is oscillatory rather than bound, and there is no gap between the positive and negative energy spectra, as in the Klein paradox. More accurate calculations taking into account the effects of the finite size of the nucleus indicate that the binding energy first exceeds the limit for elements with more than 173 protons. For heavier elements, if the innermost orbital 1s, is not filled, the electric field of the nucleus will pull an electron out of the vacuum, resulting in the spontaneous emission of a positron. The Bohr model exhibits difficulty for atoms with atomic number greater than 137, as any element with an atomic number greater than 137 would require one's electrons to be traveling faster than the speed of light. Hence the non-relativistic Bohr model is inaccurate when applied to such an element. Your basics in brief. Elements in the same group tend to show patterns in atomic radius, ionization energy, and electronegativity. The lower the values of ionization energy, electronegativity and electron affinity, the more metallic character the element has. While protons define the entire charge of a nucleus and, hence, its chemical identity, neutrons are electrically neutral, but contribute to the mass of a nucleus to nearly the same extent as the protons. Neutrons explain the phenomenon of isotopes. Varieties of the same chemical element, which differ only in their atomic mass, not their chemical action. A teaspoon of degenerate neutronium gas would have a mass of 2 billion tons, and if moved to standard temperature and pressure, would emit 57 billion joules of beta decay energy in the first half-life average of 95 megawatt of power. To handle structural integrity for propulsion and navigation for spaceships designs, extracting nuclear energy, the elemental solid-state stability of the materials is not enough for structural operation safety. So, concepts of compression can control energy releases, contributing significantly to structural requirements for performances. It was theorized that extreme pressures may deform the neutrons into a cubic symmetry, allowing tighter packing of neutrons, or cause a strange matter formation. The Bohr model exhibits difficulty for atoms with atomic number greater than 137, as any element with an atomic number greater than 137 would require one's electrons to be traveling faster than the speed of light. Hence the non-relativistic Bohr model is inaccurate when applied to such an element.